Welcome to Knowledge Feast. In this, we are going to discuss the another problem which can be solved by using backtracking. So the problem is called sum of subsets. So nothing but you will be given a set of elements or set of integers. See, there are n integers, and you will be given a number, integer number. So now you should form a set such that you will have the sum is equal to this d. So that is, I have a set S1, S2 and so on Sn. I should sum up these elements such that the sum will be equivalent to d. Okay, so that is called sum of subsets problem, and this problem will be solving by using backtracking. So now, for example, you take these elements. There are 5 elements given like this: 1, 2, 5, 6 and 8, and the sum value is d. So the algorithm that we use is, what is that we do is, we start with an empty set. Initially. So pick one element from the set S. We'll pick one element from the set S, and we'll find the sum, and we'll check whether it is feasible or not. What is feasible means? So after you pick this element and you add the sum, if the sum is less than or equal to the given integer, then it is called feasible. That is, if I add I'll take one element, I add to the set that I have formed, and the sum of the total set is exceeding 9, means it is not feasible solution. If it is less than 9, means it is feasible solution. So now, if it is feasible, we proceed further. We repeat the same step. If the sum is equivalent to d, the given number, if it is equivalent to that number, we stop. That is our optimum solution. So now we'll try this with this example. I'll take this. So this is my set, and this is my sum, and this is my the decisions that I am going to take. Is that right? So now initially the set is empty, the sum is 0. Okay, so now I add one element from the set. I add 1, so the sum is 1. So 1 is less than the actual sum that they are given, 9. So it is feasible solution. Okay, now I add one more element, that is 2. So now it becomes, so 1 plus 2, the sum becomes 3. 3 less than 9, so it is feasible solution. So now I add one more element, 1, 2. The next element is 5. So 1 plus 2 plus 5, that is, the sum is 8. 5 plus 2, 7 plus 1, 8. 8 less than 9, it is feasible. Now I add the next element, 1, 2, 5, 6. Okay, 1, 2, 5 plus 6, it becomes 14. So 14 is not less than 9, so it is not feasible solution. So what is that we'll do? So now we'll remove 6. So now we'll remove 6. If I add again 8, next element, 1, 2, 5, 8, then also it is not feasible solution. So now I'll remove 8. Now I'll remove 5 also. Previously I put 5. So now I'll remove 5. Instead of 5, I'll put 6. So 1, 2, 6. So how much it is? 9. So sum is equal to 9. So this is my feasible or optimal solution. Sum is equal to 9. 1 plus 2, 3, 6 plus 1, 9. So similarly, I can try the other alternatives. Instead of putting 6, can I put 8? It's not possible. So like this, you'll be finding the sum of subsets which are equivalent to the given sum. So as we told previously, your backtracking always uses a state space tree. So now, how to draw the state space tree, for this we are going to see. So now, the elements that we had is 1, 2, 5, 6 and 8. 1, 2, 5, 6 and 8. So now first what? Okay, backtracking is based on state space tree. So now we'll try to draw this tree. We'll start with the initial state. We don't select anything. So one side is with 1, another side is without 1. So with 1, the sum becomes 1. So this is the sum value. The sum is initially 0. Without 1, the sum remains 0. So now I'll go here. After I take 1, I can go with 2. With 2, without 2. Without 2 means the sum remains 1 only. Here 2 means 1 plus 2, the sum becomes 3. So now you come here with 2, the next one is with 5, without 5. Okay, without 5 the sum remains the same. With 5 means, so 5 plus 3, 8. I'll erase this. 5 plus 3 sum is 8. So now after this I add the next element. Next element is with 6. With 6 if I add it exceeds, so I'll not do that. So now I'll go this way without 5. Without 5 I did not take 5. So instead of taking 5, can I take 6? So this is with 6, without 6. If I take 6, 6 plus 3, 9. Without 6 this remains. So this is one of my optimum solution. So this is my solution state. Is that right? Similar way you can go with all the paths. So now without 6 can I add 8? It's not possible. Okay, I'll stop here. This is my dead node. I cannot move further. So now I'll go here with 1. Without 2, instead of taking 2, can I take 5? So with 5, without 5. So with 5 it becomes 6. Without 5 it remains 1. So with 5 I have taken. So after 5 can I take 6? 6 plus 6 it becomes 12. It's not possible. Can I take 8? It's not possible. So now I'll go here without 5. Instead of taking 5, can I take 6 again here? With 6, without 6. So with 6 it becomes 7. Here it becomes, without 6 means it remains same. So now can I add anything to this? It is already 7. The next element is 8. I cannot do this. So now I'll go here with 8, without 8. Okay, with 8 means 8 plus 1, 9, and this is 1. So this is another solution for me. This is another solution. Is that right? So like this you can use the solution state space tree or state space tree, and you can find the solutions for the